All right, welcome back to the deep dive. We have a really fascinating, well, stack of papers on the desk today. And I got to admit, when I first saw the title of our main source, I almost just scrolled right past it.
I can guess which one you're talking about.
Yeah, it's called DiskANN. Fast, accurate, billion-point nearest neighbor search on a single node.
It doesn't exactly roll off the tongue, does it?
Not at all. It sounds incredibly dry. It sounds like something, only a database administrator would get excited about at 3 in the morning.
It definitely has that dense, academic, abstract vibe to it, for sure.
Right. But then I started reading the abstract, and then I got into the introduction, and I realized, wait a minute, this isn't just about databases. This is about the hidden engine that, runs half the modern internet.
It's not an exaggeration.
We're talking about the technology that decides what products you see recommended, what videos pop up in your feed, and even how these new large language models retrieve information. And the claim this paper makes is, honestly, it's kind of shocking.
It is. It's a claim that really pushes back against, a decade of conventional wisdom in computer science.
They're basically saying, hey, you know those massive, expensive server farms that big tech companies use to search through their data?
Right, the ones with rows and rows of blinking lights.
You don't need them. We can do the same thing with the same accuracy on a standard workstation that you could, buy at an electronics store.
Exactly. It's a total David and Goliath story, but for, hardware architecture.
So today we're going to tear this paper apart. We're going to get right into the methodology, the actual how behind this claim. Because the way they pull this off, it involves some incredibly clever engineering, some really elegant graph theory, and a deep, deep understanding of how hard drives physically work.
It's a masterclass in software and hardware co-design.
Absolutely. So before we get into the Vamana algorithm and beam search, and we will get deep into those, we need to set the stakes. We have to understand the scale of the problem we're even talking about.
Right, and scale is the absolute keyword here.
The title says billion-point nearest neighbor search. So let's unpack that first.
Right.
What exactly is nearest neighbor search in, plain English?
In plain English, it's the problem of finding similar things. That's it.
Okay.
I mean, think about how you use the internet. It's not just about searching for keywords anymore, right? You don't just type cat into a search bar.
No, not for a long time. Now you upload a photo of a cat.
Exactly. You upload a picture of a specific chair you saw at a friend's house, and you ask the search engine, find me other chairs that look like this. Or you're on a streaming service, you finish a movie, and the system has to figure out, okay, you liked this gritty sci-fi thriller. What are 5 other movies that feel the same way?
Or even with music. I love this song, find me more with this vibe. That's the same problem.
That is the exact same problem. And computers, well, they don't understand gritty or vintage or vibe. They understand numbers.
Of course.
So behind the scenes, every single piece of content, every image, every song, every paragraph of text, every user profile, it gets converted into something called a vector.
A vector, which is just a list of numbers.
It's a big list of numbers, coordinates really. So imagine a graph. If you have 2 numbers, you can plot a point on a flat piece of paper, right? X and Y.
Sure.
If you have 3 numbers, you can plot a point in a 3D cube, X, Y, and Z.
Okay, I'm with you.
Now, imagine you have a list of 100 numbers or 1,000 numbers. You are plotting a point in a 100-dimensional hypercube.
Which is completely impossible for a human brain to visualize.
Totally impossible to visualize, but mathematically the rules are the same. And in this crazy high-dimensional space, the distance between any 2 points represents their similarity.
So if the point for golden retriever is really close to the point for Labrador, the computer knows they're similar breeds of dog.
Exactly. And if it's super far away from the point for toaster, it knows they are completely different things.
Okay, so nearest neighbor search is just a geometry problem. You're standing at one point, that's your search query, and you're asking, who is standing closest to me in this giant invisible hypercube?
That is it. That is the fundamental problem at the heart of all of this.
It sounds so simple when you put it like that. So why do we need a research paper from Microsoft and Carnegie Mellon to figure this out? Can't the computer just, measure the distance to every other point and just pick the winner?
It can. And if you have 1,000 points, sure, it'll do that in a microsecond. You won't even notice. If you have 1,000,000 points, maybe. It's starting to get a little slow. But this paper is talking about billion-scale data sets. 1 billion points. With a B.
Okay, that definitely changes the math.
It changes everything. If you try to compare your query one by one against a billion other items, I mean, that is a colossal amount of computation. We're talking about a latency of seconds, maybe even minutes, depending on the hardware.
And in the world of search and AI, a 3-second delay is an eternity.
It's a failure. Users will just click away, the connection times out. You want the answer in milliseconds. You need it to feel instant. So the brute force method, checking every single point, is completely off the table. You need a shortcut. You need an index.
An index, like a filing system for this hyperdimensional space.
Exactly. You need a clever way to narrow down the search, so you only have to look at a tiny, tiny fraction of the data to find the correct answer. And this is where the trouble really begins. Because as the data gets bigger and more complex, more dimensions, building an efficient index becomes exponentially harder.
This is the curse of dimensionality I've heard about.
That's the one. The more dimensions you add, the weirder the space gets, and the less effective simple indexing strategies become.
So before this paper came out, let's call it the state-of-the-art era, how were the big players solving this? If a company had 1 billion images to search, how did they do it fast enough?
The standard solution, the industry playbook, was to rely on RAM, random access memory.
Because RAM is fast.
RAM is blazing fast. It is the absolute Ferrari of computer storage. Accessing data in RAM takes nanoseconds. So the standard approach was to build these enormous, complex index structures, usually these intricate graphs, and then load the entire data set, all 1 billion vectors, into the RAM.
But RAM is famously expensive. And it's small, relatively speaking.
It is shockingly expensive, and you don't get much of it. A standard high-end server might have 256 gigabytes, maybe 512 gigs of RAM if you're really splashing out, but 1 billion high-dimensional vectors. That can easily create a data set that is hundreds of gigabytes, sometimes terabytes inside.
It just doesn't fit on one computer.
Doesn't fit, not even close. So to solve this, companies had to use a technique called sharding.
Sharding?
They'd take that billion-point data set and just chop it up into, say, 20 or 30 or even 50 smaller pieces. Then they would have to buy 20 or 30 servers, put one piece of the data on each one, and run them all in parallel.
So you're telling me every time I search for a cat picture, I'm potentially activating a whole cluster of 30 computers somewhere?
Yes. You are waking up a small data center. It's incredibly energy intensive. It's remarkably expensive to buy and maintain all that hardware. And the sheer complexity of keeping all those machines in sync is a software engineering nightmare.
And that brings us to the mission of this paper. The authors looked at this situation, this whole server farm approach, and just said, this is insane. This is inefficient.
They basically said there has to be a better way. They wanted to prove that you could achieve the same result on a single machine. But to do that, they had to move the data out of that expensive limited RAM and onto the cheap, abundant storage. The SSD, the solid-state drive.
The hard drive.
The modern hard drive, right. You can go out and buy a 4-terabyte SSD for a couple $100. Storage space on disk is practically free compared to RAM. But here's the catch, the big trade-off.
Disk is slow.
Disk is so much slower. If RAM is a Ferrari, an SSD is. Well, it's not a horse and buggy, but maybe it's a reliable Honda Civic. It's great, but it's orders of magnitude slower. RAM works in nanoseconds. SSDs work in microseconds or even milliseconds.
So the conventional wisdom in the entire field was, you cannot do fast search from a disk. It is fundamentally too slow. Don't even try.
Exactly. I mean, even the documentation for which is Facebook's famous industry-leading library for vector search, it essentially says, don't put your index on disk. It will not work well.
And the authors of DiskANN just said, hold my beer.
They did. They set out to design a system from the ground up that stores this massive index on the slow SSD, but searches it as if it were in fast RAM. And to do that, they couldn't just tweak existing algorithms. They had to invent a whole new methodology.
So let's get into that methodology, because when I was reading the paper, it seems like there are two really distinct but interconnected parts to their solution. There's what I'd call the map, which is the graph algorithm they call Vamana.
Right.
And then there's the vehicle, the system that actually drives on that map, which they call DiskANN.
That's a perfect way to visualize it. You need a map that is incredibly easy to navigate, and you need a vehicle that is specifically designed to handle the terrain, in this case, the slow disk.
Let's start with the map then, the underlying philosophy. They're using what's called a graph-based index. How is that different from, say, a simpler approach, like just putting similar things into buckets?
So the bucket approach, which is technically called an inverted index, or IVF, is a lot like a directory. It's simple. It says All the blue things are in bucket A, all the red things are in bucket B. When your query comes in, you figure out which bucket it belongs to, and you only search inside that bucket.
Which sounds fast, but I'm sensing a but.
It is fast, but it's not always very accurate, especially for really high-dimensional data. The boundaries between buckets get really fuzzy and weird. A graph approach is completely different. It's not based on sorting, it's based on navigation.
Okay, explain that.
Imagine you're dropped into the middle of a city you've never been to before. You're looking for City Hall. You don't have a map of the whole city, but you can ask people for directions.
Yeah.
You start at some random intersection. You see a gas station attendant. You ask, hey, I'm looking for City Hall. Which of your immediate neighbors, the intersections directly connected to this one, is closest to City Hall?
And the attendant points down the road and says, I don't know exactly where it is, but my friend at 5th and Main is definitely closer than I am. Go ask him.
Exactly. So you walk or hop to 5th and Main. You ask the same question again. Which of your neighbors is closest? And you just keep hopping from node to node and getting closer and closer to your target with every step until you finally arrive.
So in this analogy, the data points are the intersections, and the connections between them, the edges of the graph, are the streets.
Precisely. This is called a navigable small world graph. And in general, this method is way more accurate than the bucket method because you're following the actual geometric relationships between the points in that high-dimensional space.
Okay, but there's a huge problem with this analogy when we start talking about putting the city map on a disk.
A huge problem. A deal breaker, traditionally. In our city analogy, every time you stop to ask for directions, that's a memory access. If the graph is in RAM, asking for directions takes a nanosecond. It's instant. You can make 500 hops, and the whole search takes less than a millisecond. Nobody notices.
But if the graph is on an SSD,
Every single time you stop to ask for directions, you have to wait.
a long time in computer terms.
A very long time. You have to wait for the disk to go find that data. So if your path requires you to make 500 hops on a disk, your search is going to be incredibly sluggish. It's going to feel broken. It'll take seconds.
So what the authors needed was a special kind of graph, a graph that was hyper-navigable. They needed a map where you could get from the suburbs to downtown in, like, 5 or 6 hops instead of 500.
Exactly. They needed shortcuts, they needed highways, they needed express routes, and that is the very specific problem that their new algorithm, Vamana, is designed to solve.
That name comes from mythology, doesn't it?
It does. It's an avatar of the Hindu god Vishnu, who in one story was able to cross the entire universe in just 3 steps.
That is exactly the energy we need, crossing a billion-point universe in just a few steps. So, okay, let's do the deep dive into the methodology of Vamana. How do they actually build a graph that allows for such ridiculously fast travel?
It all comes down to how they choose the connections, how they decide which roads to build, and just as importantly, which roads not to build.
Huh?
Most graph building algorithms use what's called a greedy approach.
Greedy.
Yeah, they look at a point and say, who are the absolute closest points to this one? Okay, let's connect them.
Which sounds completely logical. Connect me to my nearest neighbors. What else would you do?
It sounds logical, but let's go back to the city analogy. If everyone in the city only knows their next door neighbors, and I need to get from the far east side to the far west side.
Oh, you have to play a giant game of telephone. Tell your neighbor, who tells his neighbor, who tells his neighbor, and on and on.
Exactly. You get stuck in what are called local clusters. You just take these tiny little steps. It might take thousands of hops to cross the map. To move fast, you absolutely need long-range connections. You need someone on the east side who knows a guy on the other side of town.
So Vamana is specifically designed to force those long-range highway connections into the graph structure.
Yes. And the way they do it is fascinatingly counterintuitive. It's a really beautiful piece of algorithmic design. Let's walk through the steps of the Vamana methodology.
Let's do it.
So step 1 is initialization, and this is going to sound completely weird. They start with a random graph.
Random, as in just arbitrary connections that don't mean anything.
Totally random. Every point in the data set is assigned a random set of neighbors. If you were to draw it, it would just look like a chaotic mess, a big hairball.
Why on earth would you start there? Why not start with nothing? Or why not start with the actual closest neighbors?
Great questions. If you start with nothing, you have this cold start problem of figuring out how to build connections from scratch, which is computationally hard. If you start with the closest neighbors, like we just said, you risk getting trapped in those local clusters right from the beginning.
Okay.
By starting with a random graph, you ensure one very important property from the get-go. The graph is connected. You can theoretically get from any point to any other point. It just might take a very weird, inefficient path. It gives you a chaotic but fully connected starting line.
Okay, so we've got our messy hairball of a graph. What's step 2?
Step 2 is the core of the algorithm. The iterate and prune process. They go through every single point in the dataset, one by one. Let's call our current point A.
Okay.
For point A, they run a greedy search on the current state of the graph to find a list of candidates that could be good neighbors for it. Basically, given the roads we have now, who is actually close to me?
So they're trying to fix the initial randomness. They're finding the real geometrically close neighbors.
Exactly. But here's the crucial constraint. To keep the index small and manageable, point A can only have a limited number of connections, a limited number of friend slots. Let's say it can only have 70 outgoing edges.
Right.
But the initial search might find 200 pretty good candidates. So you have to whittle that list down. You have to prune the list from 200 down to the best 70.
And the obvious greedy way would be to just pick the 70 closest ones and call it a day.
That is the obvious way. That is the standard greedy way. And that is exactly what Vamana refuses to do. This is the absolute core innovation of the methodology. They use something they call robust pruning, and it's controlled by a special value called the alpha parameter.
Okay, robust pruning with an alpha parameter. Let's break this down without the math. What is the decision-making process here? How does it choose which friends to keep and which to discard?
Okay, the best way to understand this is to picture a triangle. You have 3 points. You have point A, that's us, the point we're building neighbors for. You have a candidate neighbor, point B, who wants to be our friend. And you have point C, a neighbor we have already chosen to keep.
Okay, A, B, and C. Me, a potential new friend, and an existing friend.
Perfect. So the algorithm asks a simple question first. Is the new guy, point B, close to me, point A? If the answer is yes, a normal, greedy algorithm would say, great, add him to the list.
Right, he's close, he's a good neighbor.
But Vamana adds a second crucial condition. It asks, okay, point B is close to me. BUT, is point B even closer to my existing friend, point C?
Wait a second, so if my new potential friend is super close to a friend I already have?
Then you reject him, you throw him out.
You reject him even though he's close to me. Why?
Yes, because he is redundant. Think about it in terms of navigation. If point C is already my friend, I can get to point C instantly in one hop. And if point B is right next door to point C, then I can get to point B through point C in 2 very short hops. I don't need a direct road for me to point B. It's a waste of a precious friend slot.
I see. So it's like, I don't need to be friends with 5 people who all live in the same apartment complex. I just need one friend in that complex. And I should save my other friend slots for people who live in completely different neighborhoods across town.
Precisely. That is the core intuition. You are actively seeking out angular diversity. You want your friends, your neighbors in the graph to cover as many different directions as possible.
And this is where the alpha parameter comes in.
That's what alpha controls. The alpha parameter is a knob you can turn that basically controls how aggressive this pruning is. It sets the rule. It says, to be kept, a new point B not only has to be close to me, but it has to be significantly farther from my existing friends. The formula is basically dt dist e alpha dist e.
So by setting a higher alpha, you are forcing the graph to reject all the guys next door, and instead search for connections that might be a little bit further away physically, but provide a completely unique angle or direction.
Yes, and those unique, diverse angles are what become the highways. They become the long-range edges that allow you to jump across the entire graph in just a few steps.
That is genuinely clever. So the methodology here isn't just about finding neighbors. It's about actively curating a diverse portfolio of neighbors specifically to maximize navigation speed later on.
Exactly. And to really perfect this, the authors actually use a 2-pass approach to build the final graph.
2 passes. They do this whole process twice.
Yeah, they run the entire construction algorithm once with a small alpha value. A low alpha means it's less aggressive, so it tends to keep closer, more local connections. This builds out the local road network. It creates the basic skeleton of the graph.
So pass 1 pays all local streets and neighborhoods.
A perfect analogy. Then they run the whole process a second time, but this time with a much larger alpha. This second pass is much more aggressive. It's specifically looking to prune away those redundant local connections and force in the long-range shortcuts.
So pass 2 is building the interstate highway system on top of the local roads.
That's it. And the result is a graph that is structurally flat. It doesn't have complex layers like some other popular algorithms like HNSW, but because of this careful pruning, it allows you to traverse 1 billion points in a remarkably small number of hops. We're talking dozens, not hundreds or thousands.
Which brings us right back to the hardware problem. Vamana gives us this incredible map with highways that minimizes the number of hops we need to make. But we are still driving on a slow road, the SSD. Even with highways, if we have to stop and wait at every single exit, we're still going to be slow.
Right, you've solved the algorithmic problem, but not the systems problem. And this leads us to the second half of their methodology, the system architecture itself, DiskANN. This is where they stop thinking like pure mathematicians and start thinking like brilliant systems engineers who understand hardware.
So we have this beautiful Vamana graph. We have 1 billion points. How do they actually lay this out on the machine? They've only got a 64-gigabyte workstation.
The layout is a really smart hybrid. They admit up front they can't fit everything in RAM. That's the whole point. But they can fit something. So in RAM, they store 2 key things.
Okay.
First, they store the graph structure, just neighbor lists, for a small number of starting nodes. Think of these as the main entrances to the city. This lets you get your search started very, very fast.
And the second thing?
The second thing they store in RAM is a compressed version of the vector data for all 1 billion points.
Compressed, meaning lower quality,
Yeah.
a less precise version.
Yes, exactly. They use a technique called product quantization, or PQ. The best analogy is taking a huge, high-resolution photograph and shrinking it down to a tiny thumbnail. It takes up way, way less space, small enough to fit in RAM, but it's blurry. You can tell it's a dog, but you can't see the individual hairs in its fur.
So the fast RAM holds the blurry thumbnails for everything, and the slow SSD.
The SSD holds the good stuff. It holds the full precision uncompressed vectors, the original high-res photos, and it holds the actual neighbor lists for the entire Vamana graph, for all billion points.
Okay, so we have a fast but blurry map in RAM and a slow but perfect map on the SSD. The question is, how do we search this structure without getting completely bogged down by that disk latency?
Right. If we used a standard search, what we call a greedy search, we'd start at a node, use the blurry RAM data to pick the single best neighbor, then go fetch that neighbor's info from the disk and wait. Then look at its neighbors, pick the best one, fetch it from disk, and wait again.
That wait is the killer. It's the stop-and-go traffic that will destroy performance.
So DiskANN uses a completely different search methodology called beam search.
Beam search. It sounds like something out of Star Trek.
It's a great name. And the idea is pretty cool. In a standard greedy search, you have one agent or one searcher moving through the graph. In beam search, you have a whole squad.
A squad.
Instead of keeping track of just the one best candidate at any given time, the system maintains a beam, which is really just a list of the top, say, 8 or 16 best candidates found so far.
So we're essentially exploring 8 or 16 different paths through the graph at the same time.
Exactly. And here is the crucial connection to the hardware. When the system needs to check the neighbors for those 8 candidates, it doesn't do it one by one. It sends requests to the SSD for all 8 of them simultaneously.
Hold on, can an SSD even handle that? If I ask a drive for 8 different things in 8 different random locations at once, doesn't it just take 8 times longer?
On an old-school spinning hard drive, an HDD? Yes, absolutely. The little physical rehead would have to frantically move to 8 different spots on the platter. It would be a performance disaster.
So not on an SSD.
This is the key insight. DiskANN assumes you're using a modern NVMe SSD. These drives are parallel creatures by nature. They have no moving parts. They are built with multiple internal flash channels.
So they can multitask. They're designed for it.
They are born to multitask. You can send a request to an NVMe drive for 8, 16, or even 32 different random locations at once, and it will fetch and return all of them in roughly the same amount of time it takes to return just one. The latency is dominated by the initial setup, not the data transfer for small reads.
That is wild. It's like sending 8 shoppers into a grocery store at once to get 8 different items instead of one shopper making 8 separate trips.
That's a perfect analogy. So by using beam search, they are effectively hiding the disk latency. The total wait time for the batch is fixed, but because they are processing 8 nodes in that time instead of 1, the overall throughput goes way, way up. They are saturating the bandwidth of the drive to make up for its inherent slowness.
So the complete methodology is becoming clear. Use Vamana to minimize the number of hops you have to take, and then use beam search to maximize the amount of work you get done during the wait time for each hop.
Perfectly stated. That's the core loop.
But I still have a concern. We talked about that compressed data in RAM, the blurry thumbnails, If I'm using that blurry data to decide which 8 paths to explore next, won't I make mistakes?
You will.
If I'm looking for a golden retriever and the compressed thumbnail is so blurry it kind of looks like a yellow lab, won't I end up driving down the wrong street entirely?
You absolutely will. And that is the fundamental flaw of pure compression-based methods like some modes of face. They often cap out at around 50% or 60% accuracy, or what we call recall, because the compression errors lead them astray. They think they're getting closer to the target, but in reality, they're drifting off course.
So how does DiskANN fix this? They claim 95%, even 99% accuracy. How do they correct for those blurry thumbnail mistakes?
They use a technique that is so clever, so elegant, it feels like cheating. It's called implicit re-ranking. And honestly, this is the free lunch of the entire paper.
A free lunch. In computer science, those don't exist.
I know, it's incredibly rare, but listen to this. When the beam search decides to fetch a node's neighbors from the SSD, the drive doesn't just read the exact bytes for the neighbor list. Drives read data in fixed-size chunks called sectors or pages.
Right.
A typical disk sector is 4 kilobytes or 4 KB in size. You can't read less than 4 KB. It's the minimum chunk size the hardware deals with.
Okay, so you ask for a little bit of data, you get a whole block. You get the whole block. But a list of, say, 70 neighbors, the edges of the graph, is actually pretty small. Maybe it's only 500 bytes or 1 kilobyte at most. So if you only store the graph connections on the disk, you are reading a 4 KB chunk of data using 1 KB of it and then just throwing away the other 3 KB. You're wasting most of your bandwidth.
The shipping container is arriving mostly empty.
Exactly.
Yeah.
So the DiskANN authors had this brilliant idea. They said, why don't we just pack the full precision vector into that empty 3 KB of space?
Oh. So they tack the original high-res photo right next to the list of street addresses for its neighbors.
Yes. So whenever the system fetches the neighbor list to figure out where to go next, it automatically gets the perfect high-resolution, uncompressed data for that point too. It costs 0 extra time, 0 extra latency, because the disk was going to read that 4 KB chunk anyway.
That is just brilliant. It's exploiting the physical constraints of the hardware. It is. So immediately, as soon as that 4 KB block arrives from the SSD, they can compare the user's query to this full precision vector. They use the blurry RAM data to make a quick guess about where to go, but every single time they touch the disk, they double-check their work using the perfect data. They recalculate the true distances and re-rank all the candidates in their beam.
So it's like you're navigating with a rough, hand-drawn sketch map. But every time you stop at a landmark, someone hands you a crystal-clear, high-definition photograph to confirm you are exactly where you think you are.
And that process instantly corrects for any errors the compression introduced. That is the secret to how they can hit 95% or 99% recall. They get the raw speed of the compressed search in RAM, but the pinpoint accuracy of using the raw data from the disk.
It really is a system where every single part perfectly supports the other. Vamana builds a graph that's friendly to the disk. Beam search is a search strategy that's friendly to the SSD's parallelism. And the re-ranking data layout is friendly to the disk's sector size.
It's a truly holistic methodology.
I want to touch on one more crucial aspect of the methodology because it addresses a bit of a chicken and the egg problem. We've been talking a lot about search in the index. But how do you even build this thing in the first place?
That's a fantastic point.
If you have a billion vectors, that is hundreds of gigabytes, maybe terabytes, of raw data, if you can't even fit the final index in RAM, you definitely can't fit all the raw data in RAM to build the index.
That's a barrier that stops a lot of other algorithms in their tracks. Most graph construction algorithms fundamentally assume you can load all the data into memory at once to calculate distances and find neighbors. If you can't do that, you can't build the graph.
So how did the DiskANN authors solve this?
They used a very practical merged index strategy. It's a classic divide and conquer approach. They don't try to build the giant 1 billion point graph all at once.
Okay.
First, they take the billion points and use a simple, fast clustering algorithm like k-means to chop the data up into smaller, more manageable chunks. Let's say they create 40 shards.
And each one of those 40 shards is small enough to fit entirely within the 64 gigs of RAM.
Exactly. So they load shard #1 into RAM. They build a small, complete Vamana graph just for those points. They save that small graph to the disk. Then they completely clear the RAM, load shard #2, build its graph, save it. They repeat this 40 times.
So at the end of that process, you have 40 small, completely separate maps stored on your disk.
Right. But that's a problem. If you just glued them together, you'd have 40 separate islands. You couldn't navigate from a point in shard 1 to a point in shard 20. You'd hit a dead end as soon as you reached the edge of your shard.
You'd run out of roads.
If
So you need to build bridges between the islands.
you need bridges. The way the methodology handles this is by creating overlapping shards. When they first divide the data, they make sure the boundaries are fuzzy. So some of the points that are near the edge of shard 1 are also included in shard 2.
Ah, so there are some duplicate points on purpose.
These duplicates act as anchor points or bridge points. So when they finally merge all the small graph files into one big file on the disk, those overlapping points already have connections into 2 different networks. They stitch the islands together, so you end up with one seamless global graph, even though you never held the whole thing in memory at one time.
That is incredibly practical. It means the construction process itself is scalable too. You could theoretically use this to build an index for 10 billion points or 50 billion points, as long as you have enough disk space to hold the final product.
Exactly. They completely removed the RAM bottleneck from the construction phase and from the search phase.
Let's take a second here and look at the assumptions. Because no methodology is perfect. This entire beautiful system relies on some specific conditions to actually work, right?
It absolutely does. And the biggest, most important assumption is the hardware. We've mentioned this, but it really bears repeating. This methodology does not work on old-school spinning hard drives, HDDs.
Because of the seek time, the physical movement of the read head.
Right. The entire beam search strategy relies on getting fast, parallel, random reads. HDDs are terrible at that. If you tried to run DiskANN on an HDD, it would be painfully, unusably slow. It is fundamentally designed for the physics of flash memory in an NVMe SSD.
What's the second big assumption?
The second one is about caching. They make a very specific assumption that caching just the start nodes of the graph in RAM is sufficient.
Why just the start nodes?
Yeah.
In most systems, you'd want to cache the most popular or hot nodes, the ones that get access the most.
That's another one of the paper's counterintuitive findings. Normally, you're right, you cache the hot data. But in this kind of graph search, the hottest data is always the entry point. Every search starts at one of the medallion nodes they pre-select.
Okay.
But because the Vamana graph has all those long-range highways, the search moves away from that start node almost instantly. Within 1 or 2 hops, you are deep in a random part of the graph. And because the graph is so enormous, 1 billion points, the probability of 2 different searches happening to hit the exact same deep node is actually very, very low.
So the deep nodes aren't actually that hot at all. No single one gets visited very often.
Exactly. So trying to cache them is a complete waste of precious RAM. They found that the most efficient strategy is to just cache the launchpad, the start nodes in RAM, and then trust the SSD's parallelism and the beam search for everything else.
It is just ruthless efficiency at every single level.
It really is.
So let's do some head-to-head comparisons for a minute. If I'm a developer listening to this, or a CTO at a startup, why should I care about DiskANN compared to the other big names out there? We mentioned Face from Facebook and another popular in-memory one, HNSW.
Okay, so if your data set is small enough to fit comfortably in RAM, if you have 1 million items or maybe even 10 million, just stick with an in-memory solution like HNSW. It's going to be faster. Nanoseconds are still faster than microseconds. DiskANN is designed for when you hit that memory wall.
When you cross into the hundreds of millions or billions of points.
Right. When you cross into that billion-scale territory, your choice is usually to either heavily compress your data to force it into RAM using something like Face's IVFPQ mode, or to shard across many machines.
How does DiskANN compare to the compression route?
If you use heavy compression, you are sacrificing recall, which is just another word for accuracy. You might only find the true best match 60% of the time. The paper shows these methods really plateau. DiskANN, because of that implicit re-ranking, gives you 95% plus recall. So if accuracy really matters, if showing the wrong product recommendation costs you real money, DiskANN wins, hands down.
And compared to the sharding approach, just buying 30 servers and throwing money at the problem.
The 30-server cluster will give you high accuracy and high speed. It's a great solution if you have the budget, but it costs 30 times as much in hardware, power, and maintenance. DiskANN matches the accuracy of that massive cluster and comes very, very close on speed. We're talking a few milliseconds of difference, but it does it on one single node.
So the comparison there is just strictly about ROI, return on investment.
And complexity. It really is. And that gets to the democratization angle of this work.
That's the so what, isn't it?
That's the so what for me, absolutely. Before this paper, if you wanted to do high-quality, billion-scale search, you needed a big tech budget. You needed a whole infrastructure team just to manage your search cluster. With DiskANN, A researcher in a university lab, a startup working out of a garage, or even a dedicated hobbyist can now do billion-scale search on a high-end gaming PC.
That completely changes who gets to play the game to the highest level.
It absolutely does. It massively lowers the barrier to entry for building the next generation of high-end AI applications.
So as we start to wrap up this deep dive into the methodology, let's recap the secret sauce. If a listener wants to explain this to their team in a meeting tomorrow, what are the key takeaways?
I'd break it down into the two main components we talked about. First, there's Vamana, the graph construction algorithm. The key there is robust pruning, using that alpha parameter to prioritize angular diversity. This is what builds the highways in the graph that let you navigate a billion points in just a few dozen hops.
Okay, that's the map.
And second is the SSD-aware system. It uses beam search to saturate the disk's parallel bandwidth, which hides the latency. And it uses implicit re-ranking, packing the full data into the empty space in a 4 KB disk sector to get perfect accuracy, basically for free.
Vamana builds the efficient roads. DiskANN drives a whole search party in a fleet of cars to make sure it never gets lost.
That is the perfect summary. It's a perfect marriage of algorithm and system design.
I want to leave everyone with a final thought to chew on. We've been talking about vector search today, but the core underlying idea here is about treating an SSD like it's just slow RAM.
Right.
If we can effectively expand our machine's working memory by a factor of 100 just by being clever with our data structures and access patterns, what else can we solve on a single machine?
That is the really provocative question, isn't it? We usually assume that big data problems require big supercomputers, massive clusters, but maybe for a certain class of problems, we just need smart data structures.
Could you train massive neural networks this way? Paging parts of the model in and out from the disk.
Or run complex physics simulations that were previously impossible on a desktop. If you can successfully hide the latency of the disk using parallelism, that hard line between memory and storage starts to get really blurry.
And when that line blurs, the amount of computational power available to the average user, the average innovator, just explodes. This has been a truly fascinating look into the plumbing of modern AI. Thank you for guiding us through the vectors, the sectors, and the robust pruning.
It's always a pleasure to explore the cutting edge. This was a fun one.
And thank you for listening to The Deep Dive. We'll see you next time.